Hi friends, so in this particular video what I'm planning to do is talk a little bit more about iron carbon phase diagram. I told you they are the most relevant binary phase diagrams, so why don't we spend some more time discussing a few relevant things about iron carbon phase diagram. So we saw the phase diagram. See, in this particular phase diagram, we discussed about four different phases: this alpha phase, the gamma austenite phase, which then we talked about the delta ferrite phase, then we talked about the cementate phase. So let's bring all these to whatever I've discussed in the last video point by point wise. So the first three in the list, alpha ferrite, gamma austenite and delta ferrite, these three are basically solid solution. Basically they are interstitial solid solution, as our carbon atom is very small in size compared to an iron atom. The kind of solid solution which these two materials will form is of interstitial type. And the cementate, which occurs on the right extreme, is an intermetallic compound. It is a metastable product. So these were the four different phases at a glance. Now let's go into one by one. Starting off with alpha ferrite, we told that it is stable at room temperature. It is pretty evident from the phase diagram also. Then the crystal structure is body centered cubic. Maximum solid solubility is 0.08% carbon at a temperature of 727 degrees centigrade. One thing, or what I would like to bring your attention into this particular thing, I'm writing weight percentage of carbon. I'm not writing weight percentage of iron carbide. So this should be taken into account, or this should be treated with a pinch of salt. Moreover, it is magnetic below 768 degrees centigrade. This is the Curie temperature I was talking about. Then talking about the mechanical properties of alpha ferrite, it is relatively soft. Moving to the next phase, which was gamma austenite phase. So gamma austenite phase is formed after a polymorphic transformation. I already explained you, because the crystal structure changes from body centered cubic to face centered cubic. Moreover, maximum solid solubility increases to 2.11 weight percentage of carbon at a temperature of 1148 degrees Celsius. The main reason for this is the change in crystal structure, because once the crystal structure changes to face centered cubic, then you have a lot more locations or lot more interstitial spaces in FCC structure. So that's the reason why it shows a large increase in this amount of solid solubility. Then it is non-magnetic and it is not stable below a temperature of 727 degrees centigrade. It is also very evident from the phase diagram. It is ductile and it is having good formability. That's why this particular phase is very, very important when we talk about heat treatment of steels. And finally, it is denser than ferrite. Moving to the next phase, it is delta ferrite. We saw it on the left topmost portion of the phase diagram. It is a unstable product. It is only stable at a very high temperature, that too for a very narrow region in the phase diagram. It is pretty much similar to alpha ferrite, and the crystal structure is again BCC, but it is of not much of physical relevance to real life applications. So as engineers, we are not bothered about this particular delta ferrite phase that much. Now moving to the last and the final phase, but it's not the least, it's very important. So we talked about cementite, which occurs on the right extreme of your phase diagram. The composition is 6.7 weight percentage carbon, which can be also thought of as 100 percentage iron carbide. The mechanical properties of this particular microstructure goes like this. It is very hard and brittle, so that's a reason. So because of that particular reason, the presence of this particular phase will attribute strength to many of the steel alloys, not steel alloys, to many of the alloys, iron carbon alloys. Then it's an intermetallic compound, it is a metastable product, and all those things we have already discussed. So what I was trying to do by the last 5 minutes was bringing everything together, which will be pretty useful when you're giving an examination. I always do this. Whatever we have learned over a course of time, let's try to make them into folders, like what I have shown here, like 4 folders. Okay, now finally, before we wind up this video, I would like to talk about eutectic and eutectoid reactions in an iron carbon phase diagram. Before I go and explain you eutectic and eutectoid reactions, let us identify the two phase regions in this particular phase diagram. So this is a single phase region, this is a single phase region, and this is a single phase region. This is also a single phase region. Now the two phase regions are the important two phase regions I am talking about. The two of them are here. One is this particular region where both alpha ferrite and cement phases coexist, and the other important two phase region is this, where the gamma austenite phase and the cementite phase are coexisting. So these are the two important two phase regions in this particular diagram. I told you that this is the eutectic composition in this particular phase diagram. And if you are wondering why is this particular thing the eutectic point, the answer or the description goes like this. For the time being, let's say my composition is this. Then if you want to melt this particular alloy, then you have to heat it till a temperature of this much, and similarly, if your composition is somewhere here, then also you need to heat your alloy to a temperature this high, so the composition at which the alloy can be easily melted, or in other words, the composition in which I have to heat the alloy to only a low temperature compared to other compositions, is this one. Here I just wanted to heat only up to this temperature. After then I'm getting a liquid phase. So that's why this particular composition is called a eutectic composition.